This one is 3.19. Here we have a rocket that is going through this wind gust loading during the vertical ascent. Now the rotation of the system may be prevented if the resultant movement above the center of mass of the system completely becomes zero. Now this can be achieved by adjusting the thrust vector that is right here at the bottom with this angle right here. So basically in the first part we need to find out a relationship between the thrust and the wind gust loading that is given here. So let's try to find the moment above the center of mass so that we can put that equals to 0. So there are these uniformly distributed loads. So for example this one right here, it is acting at a distance of L by 4. So we can replace it by a point load with P naught times L by 4 right at the center. Now this one right here, the value of distributed load for this is 2P naught. It is acting at a distance here which is L by 2. So we can write this as 2P naught times L by 2, which is equals to P naught times L. Now the last segment here, your distributed load is 3P naught acting for a distance of L by 4. So you can replace this again with 3P naught times L by 4, and all of these are right at the midpoints of their distance on which they are acting. Now if you divide this thrust force into two components, you can have your cos component here, T cos alpha, and your sine component that's going right here. So let's take the moment about the center of mass right here. So we are going to have this force and this force right here, they will give you anti-clockwise movement, and this one right here will give you clockwise movement. So T sine alpha is sitting at a distance of L by 2. This force right here is sitting at a distance of L by 2 minus half of L by 4 here. So this is L by 8, which is equals to 3L divided by 8. And likewise, this force right here is also sitting at 3L by 8 from the center of mass. Let's write that equation for moment balance. Your T sine alpha times L by 2, this is anti-clockwise, plus this force right here, P naught L divided by 4 at a distance of 3L by 8 equals to this force which is giving you clockwise movement. So 3P naught L by 4 times 3L by 8 in this case. So if I simplify this relationship, I get T sine alpha is equals to 3 times P naught L divided by 8. So this is the answer to your part A. Now in the second part, we have to figure out the shear force and bending moment at L by 4 and 3L by 4. So your L by 4 section is somewhere here and your 3L by 4 is right here. So let's draw this part first, which is at L by 4. So if I draw this separately, on this L by 4 section, we have this distributed force because of wind. Intensity is P naught and this length is L by 4. So if you think in terms of your shear force and bending moment MB here, I can replace this uniform load with a point load with the value P naught L by 4, and since this is going to be right in the middle, both of these lengths are going to be L by 8 and L by 8 from these sides. If I do the force balance here, I get V value at L by 4 equals to P naught L by 4, and your MB value at L by 4 is going to be minus P naught L by 4 times L by 8, so L square divided by 32. So this is your shear force and bending moment at L by 4. Now if I go here, so in this segment we are going to have this force and we are going to have this force. So if I draw this, so for L by 4 we are going to have your P naught force, and for the next one we have 2P naught force. Now you can see the distances. This one here is acting for a distance of L by 2. So this right here is L by 4 and this one is L by 2. In terms of unknown, we'll have again your shear force and bending moment here. We can replace these forces with point loads. So this becomes P naught L by 4, and this one right here, 2 P naught times L by 2 becomes P naught L. This distance from here to here is going to be L by 4, and from here up to here this distance is going to be L by 2 plus L by 8. So this is going to be L by 2 plus L by 8. So when I do the force balance, I get V at 3L over 4 equals to P naught L by 4 plus P naught L. So it becomes 5 P naught L divided by 4, and your MB value at 3L by 4 is, so this will, if I take moment about this point, I'll have minus sign because both of them are in the same direction as MB. So your P naught L by 4, this is sitting at this distance, which is going to be 5 by 8L. So we have 5L by 8 here, and this force right here, which is equivalent to P naught L, and the distance for this is L by 4. So we will get L by 4 right here. So if I simplify, your MB at 3L over 4 is equals to minus 13 divided by 32 P naught L square, and the shear force we have already calculated, which is 5 P naught by 4. So these are the shear force and bending moments at 3L by 4.